In the last lecture, during your application exercise, I had you practice deriving the hat matrix, and I had you take the derivative as part of that. And I want to just mention that application exercises are basically check or no check. So their completion grades, I'm not grading it for accuracy. And the point in this case was for me to sort of gauge a little bit kind of where everybody was in terms of matrix manipulation, taking derivatives of matrices, and things like that. And also, I think it's just good practice to do this kind of thing over and over again so that it becomes kind of second nature. And I noticed that I think, in particular, taking derivatives of matrices was something that some folks maybe haven't seen a lot before. And so I thought we would just slow down and go through this kind of at a slower pace today. And so this lecture is going to be the same kind of based on deriving the hat matrix, but it's going to pepper in some matrix facts along the way, and it's going to give you a chance to kind of slowly build up to this. And so I have different sections where I have a timer that I'm going to stop. I'm going to pause for you to work through each of these pieces. And what I want you to do is I want you to work through them go ahead and open up RStudio and work through each of these in LaTeX as you go, so that by the end of the document you have a full derived hat matrix with all of the steps shown as we stepped through them that you can then turn in for today's application exercise. And hopefully we'll kind of learn something along the way. If this is total review for you, hopefully it's also just helpful to be able to gain some practice in kind of doing these derivations, because I think practice kind of helps us to be better at them and to be able to sort of recognize some of the tricks along the way. Okay, so in linear regression, what is the thing we're minimizing? How can I write this out in matrix form? And so this was in my deriving the hat matrix video from last week, but we're minimizing the residual sum of squares. And you can write this in matrix form as y minus x beta transpose times y minus x beta. And so this y minus x beta, that's our residual. And in matrix form, basically when we're squaring things, this is like epsilon here, and this is epsilon here. And so we end up with epsilon transpose epsilon. And so what is the solution to this beta hat? That's the thing we're solving for. Y and x are both, this is data that we have. So we have numbers for our y vector. We have numbers in our x matrix. And the thing that is unknown here is the beta, this vector beta. So how do we solve for that? So just to give a sneak peek to the ending here, the solution is x transpose x inverse x transpose y. But let's actually derive that ourselves, and then we're going to morph that into the hat matrix. Okay, so what is x? So x is the design matrix, and we talked about this in the last class and in the lab where you created the design matrix. And so the design matrix is a matrix that has ones as the first column, and then each of the subsequent columns are each of the x variables in your model, so each of the predictors in your model. So the second column would be the first x variable, the first predictor. The third column would be the second predictor. The pth column would be the p plus 1 column, because we've got the first one, would be the pth predictor. And as a reminder, that column of 1s at the beginning, the reason we have that is because we have an intercept in our model, beta 0. And so we want to be able to incorporate that intercept, and so we need to have this column of 1s appended to the beginning of our predictor matrix. Okay, so here is a matrix fact that we're going to be using. If you have some matrix C that is equal to matrix A times matrix B, and you take the transpose of C, it swaps the order when you pull that transpose through. So C transpose is going to be equal to B transpose times A transpose. So if I was starting with A times B, I end up with B transpose times A transpose when I take the transpose of that matrix. So we're going to use that fact to be able to distribute this residual sum of squares equation. And so what I mean by distribute is basically FOIL. I think hopefully this is somewhat familiar to you all from algebra, but basically I want you to take, like, for example, this y and multiply it by this y. That would be the f, or the first part of FOIL. And so just to tell you what that's going to get, because this is transposed, it's going to end up y transpose times y. So that would be my first term. And so I want you to distribute the rest of these out so that we basically get rid of these parentheses. So I'm going to give you about 2 minutes to work on that. Go ahead and derive that in your RStudio R Markdown document. Go ahead and try to do it in LaTeX so that we can kind of practice using that technology. And then we'll go through the answer at the end. Okay, so we're going to end up with y transpose y. That's when we multiply this y times this y here. We've got this transpose because this first part was transposed. And then we're going to have beta transpose x transpose y. So the order of these switched when we distributed this transpose, just like this matrix fact up here. So we end up with beta transpose x transpose, and we multiply that by this first one here, y. And then we're going to end up with y transpose, so that's this y transpose times x beta hat. And then finally, this beta transpose x transpose here times x beta hat. So that's how we would FOIL that out. Now I've got another matrix fact for you, that is that the transpose of a scalar is a scalar. So what do I mean by that? Well, a scalar is like just a number. So for example, the number 5. If I take the transpose of the number 5, it's still just 5. Transpose basically means that we're flipping the dimensions of a matrix. So for example, if I had a vector that was p by 1 dimensions, and I took the transpose, I would have 1 by p as my new dimensions. Well, if I have a scalar, it's just 1 by 1, and if I take the transpose of it, it's still going to be 1 by 1. Nothing's going to change. So the transpose of a scalar is a scalar. Why does this matter? Well, it matters because beta transpose x transpose y is actually a scalar. And so why is that? Well, that's because beta transpose here, this is a 1 by p by p plus 1 matrix, or a vector rather. So this is going to be 1 by p plus 1. X transpose is p plus 1 by n, and y is going to be n by 1. And so if we have those dimensions, when we cancel out all the pieces in the middle, we end up with just 1 by 1. So this here, once we multiply all these pieces together, is just 1 by 1, or a scalar. And so what that means is that y transpose x times beta hat, if we transpose this whole thing, we end up with beta transpose x transpose y. So these two are going to be equal because this is a scalar. And because scalars, if we transpose them, are equal to themselves. So what does that let us do? Well, that lets us combine these two terms here in the middle, which makes things a little bit easier. And so if I combine these two terms, I end up with 2 beta transpose x transpose y here. So now I've got 3 terms that I need to deal with in this new foiled formula. So all I've done is basically taken this and I've just rearranged it such that it's going to be easier for me to take a derivative. Okay, so that sort of gave away what this next step is, but to find beta hat, the beta hat that's going to minimize this residual sum of squares, what do we need to do? We need to take the derivative and set it equal to 0. Now this y here is important, and I think it's good to understand why we do this. So if this is not something that you fully understand, kind of think back to your calculus days about why when we're trying to minimize something, we need to take the derivative and set it equal to 0. There's a second step here is determining the second derivative, whether it's positive or negative, to figure out if we're at a local maxima or a local minima. But in this particular case, I promise you that when we set it equal to 0, it's only going to be a minimum. So we don't have to go through the second derivative, although if you would like to, you're welcome to try it. So, and this makes sense because if you think about what the derivative is, it's basically the tangent line. And when you have, let's say we have like a hill where we're trying to find the maximum, or we have basically a U shape where we're trying to find the minimum. The point that's going to be the very minimum of that is going to be where if you drew a straight line right across the bottom, it touched that point. And so we're trying to basically find the point that connects with this straight line, which is going to be equivalent to taking the derivative and setting it equal to 0. Okay, so we've got some matrix facts about how we take derivatives of matrices, and taking derivatives of vectors and matrices is very similar to how you would take derivatives of scalars. The thing that I like to remember is that when you're multiplying these, the transposes, the main purpose of a transpose is basically to make things conformable. And so by conformable, I mean the inner parts of your dimensions need to match in order for matrices to be able to be multiplied or vectors to be able to be multiplied. And so that's what the transpose is doing. And so don't let it kind of confuse you otherwise. If we covered up this transpose, and we did, and you just had scalars a times b, and you were taking the derivative with respect to b, I think it would be pretty easy for you to see that that's just a. We know that. That's just a derivative fact. And similarly, if the b was on the other side, so if it was b times a, the derivative was with respect to b, we would still have a as our answer to that derivative. So the same thing holds for matrices and vectors in this case. Another piece of information that's important to know is that if we have 2 of the same vector, so for example here, B is a p by 1 vector, A is a symmetric matrix in the middle. If we're taking the derivative with respect to B, it's going to be just like in normal kind of scalar mode, where if we had B times A, which would be like having B squared times A, if we took the derivative of B squared times A, we'd end up with 2AB. That's essentially that I think is kind of makes it a little bit clearer to see. So what I want you to do is go ahead and try to take the derivative of this thing that we just calculated with respect to beta hat. So I'm going to give you 2 minutes to do that. So you're going to want to take the derivative of each of these pieces with respect to beta hat using these matrix facts. All right, let's see how we do it. Okay, so if I take the derivative of y transpose y with respect to beta hat, what would that be? Well, that's 0 because there's no beta there, so we can just not pay attention to that. The next part is this negative 2 times beta transpose x transpose y. So this is like that first matrix fact where we've got beta transpose some vector multiplied by 2 plus some other kind of pieces here. And so basically what's going to happen is that's just going to cancel out this beta hat. So we end up with just negative 2 x transpose y. And then this third piece is going to follow that second piece of matrix advice where we have beta transpose x beta, which kind of is like having a beta squared in this. And so we end up with 2 x transpose x times beta. So there we've got this. We're going to set this equal to 0 and solve for beta. Here's another matrix fact. A times A inverse equals I, where I is the identity matrix. So we're going to be using identity matrices a good amount in this class, but the identity matrix is basically a matrix where there are 1s on the diagonal and 0s everywhere else. And so this is kind of like the matrix form of multiplying by 1. So if you multiply A times the identity matrix, you just get back A. So any matrix multiplied by the identity matrix will just give you back the matrix itself. And so that fact you're going to be using in a second, but what I want you to do is I want you to rearrange this equation to solve for beta hat. Let me give you a couple minutes to do that. All right, so let's look at that. So the first thing I'm going to do is I'm going to move this over to the right-hand side here and cancel out the 2's. So this gives us that equation that basically we started with in the video that I posted last week for deriving the hat matrix. So we end up with x transpose x beta hat equals x transpose y. So now we just need to move this x transpose x over to this side so that we have just beta hat on the left. And we can do that by basically taking the inverse of x transpose x on both sides. And if you remember from that matrix fact before, if you multiply something by its inverse, you end up with the identity matrix. And so multiplying something by its inverse, I mean, this is sort of like in scalar form where you divide by itself. So if you have x divided by x, it's just going to be 1. So this is kind of the same format here. Important point here is that x transpose x must be invertible. So it must be possible to take the inverse in order for this to be the case. And this is a key limitation of linear regression in general, least squares in general. But as long as we can take that inverse, this is how we would do it. And so then we end up with the identity matrix times beta hat equals x transpose x inverse x transpose y. And from that matrix fact, we know that the identity of matrix times anything is just that thing itself, so we can get rid of that identity matrix, and we show that beta hat is X transpose X inverse X transpose Y. Okay, so now we've solved beta hat. The big goal here was to get the hat matrix, and so we've got one more step here along the way. So the hat matrix puts a hat on Y. So basically, when you multiply this hat matrix H times Y, you end up with Y hat. So what is Y hat? Well, Y hat is X times beta hat. We know that's true. And what is beta hat? Well, we just solved it. It's that X transpose X inverse X transpose Y. And so Y hat is just going to be X times X transpose X inverse X transpose Y. So the hat matrix is going to be all this part before Y. The hat matrix is X times X transpose X inverse X transpose. So there you have it, derivation of the hat matrix, step by step. Hopefully you've been able to sort of get this written up as we're going along. If you could turn in this application exercise as an HTML file on Canvas, that would be great.